This presentation is about understanding the basis for deriving the expression for the speed of sound. Newton initially derived the equation for the speed of transverse waves on a stretched string. He derived the velocity as the square root of the ratio of the tension imposed on the string, tau, or this stylized t, divided by the mass per unit length of the string, mu. So Vt, the subscript t stands for the transverse wave. Transverse wave velocity that Newton found out, Vt, is equal to square root of tau by mu. Tau is the tension and mu is the mass per unit length of the string. Newton then extended this formula to the case of sound waves in gases. So from stretched string, he extended it to the case of gases and derived the new formula, Vt equals square root of pressure of the gas, P, divided by the density of the gas, rho. So this is for gases, Vt equals square root of P by rho. This is basically just a reframing of the original equation, Vt equals square root of tau by mu. So basically if we divide top and the bottom, tau by A and mu by A, where A is the cross-sectional area of this system, this spring mass system, then we get tau by A is just pressure, force per unit area, and mu by A, the mass per unit length divided by cross-sectional area is mass per unit volume, which is density. So just like this is a very simple extension. So he extended from this tau by mu to P by rho, the formula for the speed of sound. So, but Newton himself had recognized that this formula is an underestimate because of the experimental evidence available at his time. This formula is valid for transverse waves only, and sound is not a transverse wave. So even without any experimental evidence, we may claim that this theory does not match the sound propagation phenomena. Sound is a longitudinal wave, and this theory is for transverse waves, hence incompatible. We will not go into more details of the many other kinds of inconsistencies we get with this concept or while deriving this formula. For longitudinal waves on a string or through any solid or fluid, we get a different expression. The velocity we get is equal to the square root of elastic modulus, epsilon, or rigidity modulus. This is the epsilon is the rigidity modulus or the elastic modulus divided by density rho. So VL, subscript L stands for the longitudinal waves here. So VL equals square root of epsilon by rho, that is rigidity by density. So this is for the longitudinal waves on a string or any solid or fluid. So this new equation is equivalent to Laplace's derivation of the speed of sound in gases. Basically, Laplace modified this Newton's formula from square root of P by rho to square root of gamma P by rho. He introduced this new factor gamma, which is the ratio of heat capacities. So gamma equals Cp by Cv. And thus he corrected the underestimation error in Newton's formula. We shall note why even this Laplace's formula is conceptually not the correct way of looking at the speed of sound. Even though the formula matches the speed of sound in gases under various conditions, the theory and any of the way this formula can be derived is not entirely sound. The best way to derive these expressions might be to explicitly utilize the implicit analogy used between wave propagation in a gas and spring mass chains. So for longitudinal waves, from the analysis of the spring mass chain normal modes, we get the approximated velocity at the first few normal modes when there are an infinitely large number of spring mass units. So this is an approximation which is valid in only in the first few normal modes when there are a large number of spring mass units. So then the longitudinal wave speed on this spring mass chain can be written as VL, the longitudinal speed, equals L into square root of K by M. Here this the subscript refers to the longitudinal waves, but this alphabet L refers to the resting length of the springs when they are not disturbed. So each of this spring has a resting length of L, capital L, and K is the spring constant, and M is the mass of the particles in between these springs. All these circles in violet color, these are all the mass particles, and they have mass M each. So VL equals L into square root of K by M. So this is the speed. In reality, it has a dispersion, but in the first few normal modes, we can ignore it. For gases, we can define a system equivalent to the spring mass chain in which the gas is compartmentalized into smaller subregions. The figure shows gas molecules in orange, this top figure, with imaginary boundaries between these groups of molecules shown in dashed black line. So one region is compressed, it is a smaller region, one region is rarefied, it is a bigger region, the volume is bigger, and so on. So this is how we assume that the gas looks when the sound propagation is happening. There will be some regions with compressed region, higher density, lower volume region, and there will be a rarefied region with higher density, lower density. So we imagine the mass of the gas molecules as concentrated in the pistons in orange, shown in the below figure. So basically all these mass, individual particles, their mass, we assume that they get concentrated in these pistons or these bars shown in orange in the below figure. And in between the pistons, in between these bars, we assume that the region is occupied by massless springs, shown by these zigzag lines. If there are total n free gas particles in the system of mass m naught each, then the total mass of the gas is m naught into n. N is the capital N. If the gas particles are separated uniformly by n Plancks, small letter n Plancks of mass m each, then the total mass of the Plancks is m into n. We assume that the total mass of the gas is equal to the mass concentrated in the Plancks. Therefore, this big M, which is the total mass of the gas, supposedly, should be equal to m naught n, which should also be equal to m into n, because the total mass of the gas we assume is to be concentrated in the pistons. So we assume those particles are massless. All their mass has gone into these edge boundaries or the pistons, and in between the region is composed of massless springs. Suppose in the initial undisturbed state, when there are no compressions and rarefactions, the pressure is P and volume of the compartments is V. So each of these compartments, suppose in the resting state, has volume V and pressure P. Suppose the initial compartment length is L and the cross section area of these compartments is A, capital A. So the volume of each compartment initially in the undisturbed state is V equals AL. And the compartments are separated by Plancks of mass m kg each, as assumed earlier. So the in-between region is composed of massless springs, as discussed earlier. So when we do this, take this analogy, when we do the force balance equations for these pistons and the springs in the below figure, we get this kind of formula. So basically, while doing the force balance equation, we also assume that the adiabatic condition holds. So that is why we assume Pi Vi power gamma is nearly equal to P of V of power gamma. So PV power gamma as a constant, we assume that as a constant, assuming this is an if this is an adiabatic process, we assume that. So along this, so while using the force balance equation, solving them, we use this condition PV power gamma. Then we get a system where this below system has a spring constant equivalent to gamma PA by L, where P is the undisturbed pressure, A is the cross section area, and L is the length of these compartments in the undisturbed resting state. Actually, we can also derive the Newton's formula from the same method using the same equations, same force balance equations. Only instead of PV power gamma equals constant, we just assume PV equals constant, which gives the isothermal condition. So if we just take PV equals constant, we get the isothermal condition where implicitly gamma equals 1. Or if we take PV power gamma equals 1, where gamma is not 1, which is the specific heat ratio of the specific heats, then we get the spring constant as gamma PA by L. Otherwise, we get for the Newton's formula, we get there will be no gamma factor here. It will be just 1 PA by L. So this is what the spring constant we get. Also note that the applications of PV power gamma and PV equals constant, these things are not actually physical. That we have shown in the last video that we cannot use this, but mathematically it's possible. We can use these to solve the force balance equations. Along with the force balance equations we can use, so we can just use it mathematically, but physically as such it does not make sense. You can watch the previous video for more details. So basically, what happens is the longitudinal wave speed we know as L into square root of k by m, and k we know as gamma PA by L from this analogy, using this analogy. So we get the speed as gamma PA L by m. So gamma p remains in the top in the numerator, and the denominator we can replace this m by Al by some quantity called density, which density is this m divided by this compartment volume. That is what we get. So that we can represent as density. So this is the expected kind of formula for the speed of sound, the Laplace's kind of formula, which we get by using this analogy and also using this adiabatic condition, and then solving the force balance equations that we get from this. But in reality, if we conduct any real-time experiment, a real experiment, then both the gas particles and the pistons will have some mass. We cannot just assume that gas particles are massless and all their mass is concentrated in the pistons. In general, we cannot assume that the net Planck or the piston mass divided by the total volume will give the same density as the density of the gas particles. That is rho m. Rho m, we call it as the density of the Plancks, basically calculated using this mn is the net mass of all the Plancks, divided by NaL is the total volume of this gas piston system. So when we divide the net mass of the Plancks or the pistons divided by a total volume, we get some density kind of quantity, which we will call the density of the Plancks. And the other one, just rho, equals m naught n by NaL, which is just the density of the gas particles. So when in the equations that we derived, what we get is in the wave equation that we derived, what we get is the Planck density, this rho m. We are not getting the gas density because we are using the Planck masses. The Plancks are the ones that are oscillating, and those masses are the ones which get into this oscillatory equations. So dissociating the gas pressure from the gas mass is not a realistic assumption. Those Plancks separating the compartments are external items in the gas. They are moving back and forth due to the pressure exerted by the particles of the gas on them. So we cannot just ignore the mass of the gas because they are the ones exerting the pressure. The mass is responsible for that. That gives the momentum. So here we may not need these artificial conditions like m equals mn equals m naught n, where mass of the gas is equal to mass of the piston. That is an artificial condition. We will not need that. This equation will work even without that, and also that there is no correlation between m naught and m. The mass of the Plancks and the mass of the gas particles, they are not correlated in any way. They are not bound by any condition. They are independent. They can have any values. So in that sense, the speed of sound we get from these kind of derivation, from the analogy between this spring mass chains and this gas particle system, gas piston system, is V equals square root of P by rho m, which is in general not equal to gamma P by rho, square root of gamma P by rho. For example, if the Planck density is greater than the gas density, then the velocity of the sound or the signal propagation in this system will get as less than the speed of sound. If Planck density is less than the gas density, then what we get is the velocity of signal propagation in this piston system we'll get is as the more than the speed of sound. So basically, if the Planck masses are 0, if m equals 0, this v becomes infinity. Because if the Plancks are very thin and very low mass in this gas, then we can get a very high signal propagation velocity in this system. So basically, that is by using various Planck masses, we can achieve a wide spread in the wave speed or the signal propagation speed. And this situation does not particularly tell anything about the waves or the energy propagation by the particles of the gas themselves, independent of the Plancks. It doesn't say it doesn't describe the situation independent of the Plancks. All it shows is the effect of the gas particles on the external Plancks. So having these spring-mediated interactions between gas particle masses is not compatible with the signal propagation velocity that we would derive using a kinetic theory of gases. Basically, this kind of situation is not compatible with the kinetic theory of ideal gases, where we assume that there is no long-range interactions between the particles. Ideally, there should be no long-range interactions between these gas particles. If at all, if there is any long-range interaction that exists, then it should be resolved between those individual gas particles and not by some arbitrary grouping of particles as shown in this above figure. However, if we want to observe bulk oscillations of pistons in such a systems, we can do such an experiment with a lot of pistons separated by the gas, pistons separating the gas particles into compartments. We can do such an experiment. But in the usual experiments that we do to find the speed of sound, these kind of Planck oscillations are not what is observed. We don't have all these Planck separations and all in the usual experiments. So this is not at all what is being observed. But this kind of picture is needed to derive the equation, the Laplace's formula, in analogy with the spring mass change. So if we want to resolve the interactions between the individual ideal gas particles based only on the elastic collisions, then we should consider a situation like this as shown in the below figure. So consider elastic collisions of rigid spheres arranged more or less in a straight line. The collision need not always be collinear, but we assume this collinearity for simplicity. So all these spheres shown in the dark blue or the sky blue, these circular regions, they are the hard spheres, and they are more or less neatly arranged on a straight line so that we can resolve the collisions easily. They need not be always on a straight line. In a real case, they will not be on a straight line. But for theoretical simplicity, we assume that. Suppose we have a large cylinder filled with particles, uniformly distributed with a spacing of L0 meters between them. So this L0 depends on the density of the gas particles, and if there are a total number of n, this capital N, which is much larger than 1, if there are n particles in the system, then on an average we can say n L0 cube is nearly equal to V0, where V0 is the total volume of the gas. So these elemental volume, L0 cube in a sense shows the elemental volume. So number of particles into elemental volume n into L0 cube gives the total volume of the gas. So this is roughly it's a very good approximation. Very closely it matches. And also we should note that the size of the particles, these particles in the sky blue, is not exactly 0. They have a size, the diameter of d as shown in the figure. The non-zero size effectively alters the total length of the signal propagation. So suppose we consider a straight line of length d and a particle of size d traveling on it with a velocity vx, then the total length the particle has to travel is only d minus d. So by the time it travels this distance d minus d, the front face of this particle will touch at this edge of this line, the right edge of this line. So it has to just travel d minus d to carry the signal from this end to this end, because the size of the particle is non-zero. Similarly, if there were a lot of n such particles distributed along the whole length d, then the total distance any disturbance needs to travel to grow from one end of the line, one edge of this segment to another edge is only d minus n into d. Since they are all moving with velocity vx, the pattern of signal created at one end takes a time, this capital T equals d minus nd by vx. This many seconds to reach the other edge of the line. So, but the total length we measure is d. The total length of this segment is d meters, and the total time taken by the signal is this t seconds. So, the effective velocity of the signal propagation we work out would be v equals d by t. So, d is the total length, t is time taken. So, note that the average separation length is L naught. So using all these things in the equation, d by t becomes just Vx divided by 1 minus d by L naught. So where Vx is like the typical velocity of these particles along this axis, along this x-axis, or the average velocity of these particles. In this case, it's actually all the velocity, the exact velocity of these particles is Vx. And d by L naught is the packing ratio of the particles. D is the size of the particle, L naught is the spacing between the particles. So when so we can note that when d by L naught equals 1, then the particles are densely packed and the signal propagates at infinite speed. Or there will be some maximum limit. So basically what this needs is if there is a speed limit like c, or the speed of light, or some speed of sound through this material, so that the signal travels from one edge of this particle to the other edge of this particle itself, this hard sphere, in some time. We can practically assume it as infinite in comparison to these collisions and the movement of the particle. So it comes as infinite speed, otherwise there may be some speed limit there. So practically you can assume that it is like an infinite speed. If they are so densely packed and we disturb one, the disturbance reaches the other edge of the line almost instantaneously. We could most easily verify this model and this formula by conducting an experiment with billiard balls. As of now, we do not have an independent derivation of Vx in a gas. So perhaps we could use statistical mechanics or some other basis, basic physics, to derive an expression for Vx. And also we could measure this Vx, Vx of the actual gas particles during real sound propagation in gases. We could experimentally verify this in gases also. So in the absence of an independent derivation, we can probably estimate Vx by equating it with the Laplace formula that we already know. So because the Laplace formula matches the observations pretty well under normal conditions. So we can say V equals square root of gamma p by rho is also equal to Vx by 1 minus d by L naught. So this on the right hand side, extreme right hand side, we have this expression, the new expression, which is compatible with the kinetic theory and elastic collisions. And gamma p by rho is the Laplace formula. So basically this means when d by L naught is around 0, that is when the gas has very low density packing, then we get Vx is nearly equal to gamma p by rho. So which is the same as this Laplace formula, and we have to think about how this gamma factor comes here. So basically this is easy to explain. In this case, the gamma factor is coming from the energy conservation equation directly, rather than from the assumption of the adiabatic process. That is, this gamma factor comes from the first law of thermodynamics, adiabatic energy conservation, just from that equation, and not from assuming the adiabatic process. So the net energy E of the system initially is given by E equals F by 2 nkt plus mgz. Basically the first term, F by 2 nkt, is the internal energy term, or the heat energy of the gas, which is the temperature of the gas, contained in the temperature of the gas. And the second term is the potential energy term, or the mechanical work term of the system of this basically in the piston. We'll show it with the piston or whatever this vessel that is holding this gas at this temperature. So basically that has a potential and some kind of potential energy, and that potential energy works out to be mgz. In a normal case, we'll show that. So basically this is just the first law of thermodynamics, where we have F by 2 nkt is the heat plus mgz is the work part. And basically when we add this up, we get that the total energy is gamma into F by 2 nkt. So it is, we know it is larger than F by 2 nkt because there is this extra term mgz, and it turns out that it is gamma into F by 2 nkt. We can see this in more detail in the next page of this gas piston system. So basically in this, a cylinder is placed vertically on the surface of the earth. The piston weight is balanced by the pressure of the gas particles. So the mass, so basically we'll have these relationship: P equals mg by A and V equals Az. So P is the pressure of the gas in the initial pressure of the gas, M equals mass of the piston, G equals acceleration due to gravity, and A equals area of the cross section of this cylinder. So basically volume becomes just cross section area into height, V equals A into Z, and the pressure is mass into gravity divided by area of cross section. This is force per unit area, which is pressure. So this relationship will hold good in this cylinder system, in this cylinder piston system. And therefore we can write the net energy as E equals F by 2 nkt, which is the heat energy of the gas, plus this piston is also part of this gas piston system. So its potential energy is mgz. It is mass m, it is at a height z, and acceleration due to gravity is g. So F by 2 nkt plus mgz. It turns out to be 1 plus F by 2 nkt, because mgz turns out to be nkt. Using ideal gas relationship along with this P equals mg by A, we get nkt equals PV equals mgz. Therefore E, the total energy of this system, turns out to be 1 plus F by 2 nkt, or 1 plus F by 2 into mgz. So basically you can convert this into gamma into F by 2 nkt. This 1 plus F by 2 can be written as gamma into F by 2. So this is what we get: E equals gamma into F by 2 nkt. And we also know that this T is related to the root mean square velocity of these particles. So basically we can express E as half into total mass m into gamma into Vrms squares. So if we had ignored this gamma factor, if we had not considered this external work part, if we had just taken the heat energy of this system, we would have just got F by 2 nkt. But we have to consider the whole system. The whole energy is gamma into F by 2 nkt. So this gamma factor comes from there. And that implies that the root mean square velocity available is not Vrms. Actually, if under a condition, if this whole heat and the external potential energy term, if this whole term can be converted into, if this whole energy can be converted into kinetic energy term, then the Vrms, the RMS velocity will have this extra factor gamma into Vrms, consistent with this total energy equation. So basically, if we had considered just the heat energy part, we would just get Vrms. But in this situation where there is heat plus work, there are two components of energy available. The net Vrms can have this added factor gamma Vrms. It can have a higher, when this the whole energy available to this system is can be converted into this movement of these particles, then we get gamma Vrms as the root mean square velocity. So this is how we get the gamma factor into this equation. Basically, we have to consider both the heat and the work, both the components of the energy, not just the heat component. So this is how we get the gamma factor, and that is what makes this change from square root of p by rho to gamma p by rho. So that is why we get this. We need this extra gamma factor in this speed of sound formula. And this also implies that the component of this Vrms along any direction x, y, z will be instead of VRMS by root 3, initially it will be VRMS by root 3. So if VRMS is the total root mean square velocity, if we split into 3 components x, y, z, each will get VRMS by root 3, VRMS by root 3 and so on. But in this case, since the VRMS has an extra gamma factor, each component will also have this added gamma factor. So each component, each velocity component along each axis is gamma by square root of gamma by 3 into VRMS. So the speed of sound we can write now as V equals square root of gamma by 3 into VRMS, which is also equal to the Laplace's formula gamma p by rho. And from this collision considerations, we get this Vx by 1 minus d by L naught. So in this case, if the speed was gamma, in the normal case, we would have taken this typical x-axis velocity Vx, typical velocity or the average velocity along this any axis as VRMS by root 3. But using this equation, this speed of sound equation that we have used here, we get Vx equals square root of gamma by 3 into VRMS, and we have this extra component, extra term, or this extra factor in this square bracket 1 minus d by L naught, where d by L naught is the packing ratio. Basically, this comes up, basically this means as the density of the gas increases, the velocity along this, the velocity of these particles associated with the signal transfer. So whenever the signal is being transferred, the particles are moving with certain velocity. This effective signal transfer velocity drops because of higher density. This mainly happens because of all the non-linear collisions in the system. The number of, as the density increases, the number of non-linear collision increases. So the particle, this component Vx, which was only in one direction Vx, it gets diffused into other directions and then gets recombined and so on. So basically these non-linear collisions effectively reduce that velocity. So that is why this term 1 minus d by L naught is coming into Vx. If we derive from basic physics, from basic statistical mechanics, we may get slightly varying expression for this Vx. We may get as Vx is equal to gamma by 3 VRMS into 1 minus d by L naught to the power of beta. Instead of this exponent which was 1 here, 1 minus d by L naught, it could be 1 minus d by L naught to the power of beta. In that case, the speed of sound we get as gamma by 3 VRMS into 1 minus d by L naught, beta minus 1. In this case, if beta equals 1, this term goes off, and we just get the speed of sound as gamma by 3 into VRMS, this term. But we know that as the density of the gas increases, the speed also varies. This is not apparent from the Laplace's formula, but it is experimentally observed, and to deal with that, we use these virial equations where the ideal gas equation is supposed to break down. So basically, whatever the velocity we get from the actual statistical mechanical consideration, it might have a form of this beta minus 1, where beta may be some value less than 1, so that we get an expression which is consistent with the speed of sound, which varies with density according to these virial equations. So that we have to work out from statistical mechanics, this expression, exact expression for Vx. But nominally, from the by equating these two forms, the Laplace equation with the collision derived formula, we get Vx equals gamma by 3 VRMS into 1 minus d by L naught, which can be experimentally verified in a gas. So in a sense, Newton had anticipated this formula already, but his Vx term was square root of p by rho that he had derived earlier using this transverse wave relationship. But by using p by rho factor along with this correction factor in the denominator 1 minus d by L naught, we will not get the correct results in all the situation. Newton had almost got the proper theory of sound propagation in his second edition of Principia. We can refer to this paper by Bernard S. Finn from 1964. It discusses what other options, what other variations that Newton tried. But I'm glad Newton did not furnish the whole theory or the complete theory of this during his time. In any case, no one considers what he did useful, his later work on the speed of sound, because Laplace built on his earlier work and derived a different formula. And even this author, Bernard Finn, is inclined towards Laplaces like any contemporary physicist. And he says, for a century and a quarter after Isaac Newton initially posed the problem in the Principia, there was a very apparent discrepancy. To remedy such an intolerable situation, some like Newton optimistically framed additional hypotheses to make up for the difference. Others like Lagrange pessimistically confessed the inability of contemporary science to produce a reasonable explanation. Later, supposedly, Laplace explained it. And further, he says, the author, Finn, about Newton. So, Newton had realized that it's an underestimate, and he tried. A solution could be found in his or Newton's theory of particulate matter, particulate nature of matter. Newton proposed that the particles of the air had diameters equal to 1/10 of their mutual separation. Basically, here Newton is speaking about this packing ratio d by L naught. So this is what he is referring to here in this line. So one of the reasons why this was not accepted, maybe he depended for this on the particulate nature. Initially, he had derived using continuum nature of these fluids. But for the correction, he depended on this particulate nature of matter, and maybe he was too early to have an explanation based on the particulate nature of matter, because not until the times of Boltzmann and Einstein this particulate nature of matter came to be accepted in thermodynamics. Before that, it was all continuum. So Newton's proposal was just remained in his work. So Newton proposed that the particles of air diameter had 1/10, so that is why they get this correction. So basically, the particles would have to vibrate only 90% of the distance that he had previously supposed, or alternatively, the sound moved through the particles 10% of the distance at infinite speed. So this through the particle itself, the propagation is infinite. That is what we had also discussed earlier. So that's how we get the correction. That is what Newton thought. So we end our presentation with that. In this presentation, we saw that both the transverse wave isothermal process based Newton's derivation and the longitudinal wave adiabatic process based Laplace's derivation are both wrong ways of deriving the speed of sound. Just looking closely at these kinds of derivation, we see that they do not really correspond to propagation of sound, but they show propagation of disturbances between pistons separating the gas compartments. So it does show propagation of disturbance, but in these pistons, it is not same as the sound propagation. And because this speed, whatever this the propagation of disturbances between these pistons, this speed depends on the mass of the pistons or the mass of these planks separating the gas compartments. And we can have any wide spread of velocity around the wave velocity. It depends on the density of the planks and not on the density of the gas particles, and that is why it does not represent the sound wave. It represents the propagation of disturbance in these pistons. So both these equations are wrong for the same reasons. Even if the physics behind them is valid, actually we have shown that the physics is not valid. Even if we assume that the physics is valid mathematically, then even then they have the same weakness. That is, they represent piston oscillations. They do not represent the propagation of sound in gases without these pistons and compartments. So if in the absence of pistons and compartments, these derivations won't work. They'll not give the results. So therefore, it is likely that the correction suggested by Newton in a later work may hold the key to derive an expression compatible with the kinetic theory of gases and elastic collision. So whatever we derive, that has expression has to be ultimately consistent with the elastic collisions. And here in this formula, we just need a correct statistical way to estimate the average or typical velocity Vx observed along the x-axis. This x-axis is not, it can be in any arbitrary direction. It's in along any axis, along any direction of propagation, we can find. Possibly this is not difficult to find. This statistical way of finding how the Vx varies. Possibly a theoretical derivation is not difficult. We will try that in the future. So that is how we should go about it. So this is likely the most correct way of looking at the speed of sound. And also we can experimentally verify whether we find this value Vx when we do actual experiment with real gases, real sound propagating in real gases. So that's about it. Thank you. Please subscribe to our channel, Neophysics.